Good afternoon, everyone.
Pleasure to be here. So yes, my background, initially my PhD was on mathematics of computation. I was deeply steeped into all the algorithmic aspects of machine learning and related topics. But then I spent the last 20 years working on behavioral decision making, both in terms of executive education and research. So I find myself now in a rather unique position in that I understand fairly deeply both sides. So the conversation I want to have with you today is to bring some thoughts that I think are very important for all of us to make sense of as we think about how to navigate what's going on with AI and how to lead forward in the path that's going to open on account of it. So let me start first with this question. How are people feeling about AI? You know, who's feeling hopeful about AI? No one is feeling hopeful about AI? Okay, reasonable amount of hope. Who's feeling excited? Lots of excitement. Who's feeling anxious about it? Yeah, a good bit of anxiety. Who's angry about it? Not so much, about 4 people, 5 people. Yeah, so it's quite striking, right? Some very powerful things stirring up under the surface. It's not the same as previous technological changes we've had. This is really stirring up some very deep feelings that we need to make sense and contend with. What is striking, this is a poll of young people, Gen Z people in the United States. You can see that there's quite a bit of anger. A full 1/3 of people are feeling angry about AI. A lot of anxiety, 40%. What's even more concerning is the positive feelings. Very low excitement and even hopefulness is down to 18%, right? So we need to understand what's going on. Technology is going to be incredibly disruptive, open enormous amount of possibilities, but there's some complicated things that are happening and we need to make sense of this. So how can we lead in this environment? I would say, well, let's start from the fundamentals. We need to understand the technology, not in terms of the nuts and bolts of the machine learning algorithms, but what it actually is and how it relates to people. And fundamentally, how does the technology interact with people and with human systems? Yeah, that's a recent protests against AI. So let's do a little 10 minutes tour of the history of computation. Arguably goes back all the way to the 19th century. Ada Lovelace was the first programmer. She wrote the first computer program as we would call it today. There were no computers to execute her code, but you can take her code, convert it into a modern language and run it, and it does work. There were no computers. What was there? Do you know what these people are? Anyone has a guess of what these people are? Say again? No. These people are computers. These people are computers. If you were to ask one of these ladies, what do you do for a living? She would say, I am a computer. A computer was a job. There were bakers, then there were different kinds of jobs, and there was a computer, was a job. You calculated numbers. Calculations, accounting, logistics, ballistic trajectories for artillery shells in the army, all sorts of calculations need to be done. They were done by computers. It was a job. And then we created the machine that did that job, and we gave the machine the name of the job that it accomplished. Right, and then the first machine, arguably, that we called, at the time it was not called a computer, that we now call a computer, the Colossus at Bletchley Park, that was used to break the encryption codes during the war. Machines have gotten faster and faster over time. One of the first big successful commercial machines, the IBM 7090, was the backbone for the spaceflight program, calculating the trajectories. 100 kiloflops, that's 100,000 operations that it can compute in 1 second. Then the CDC 7600, designed by Seymour Cray, led to the famous janitor memo from Thomas Watson, the president at IBM. This machine was built by a team of only 34 people, including the janitor. Why are these guys with this tiny team beating our giant research lab? A big lesson to be drawn here. When you have this kind of big technological changes, you don't need giant teams. Sometimes what you need is a very high quality driven team to have a huge impact. Seymour Cray then left CDC, was leading this team, left CDC and started Cray Computing, designed the Cray 1. It's basically the backbone, the foundation of modern supercomputers, the first liquid-cooled supercomputer. And again, a really interesting piece of technology. Then the cryo-MP in the 1980s, the fastest machine was the cryo-MP. I think it's still the coolest supercomputer ever in terms of the way it looks. And then in the 90s, the ASCII read, this was the first one to break the teraflops. So kiloflops is thousands of calculations per second, then mega, millions per second, billions, this is teraflops. That's going to be 10 to the 12. Was the first one that could do 10 to the 12 arithmetic operations per second. It was compared at the time by the chief technology officer of Intel to the breaking of the sound barrier, to landing on the moon, major achievement. We've reached the teraflop barrier. And then the Roadrunner in the 2000s was very important because it allowed the US to feel comfortable with signing the full ban on testing nuclear weapons because we could now simulate it rather than be blowing up bombs to make sure that they work as expected. That gets into the petaflops, that's 10 to the 15. Then the Summit, and then El Capitan, currently the fastest supercomputer, was the first to break the exaflop barrier, meaning in 1 second, it can do 10 to the 18 calculations. That's a 1 with 18 zeros. That's the number of calculations it can do in 1 second. It's hard to even get your mind around of what that means. Previous holders of the crown, the Sunway Tahoe in China, the Fugaku in Japan. This was a computer designed for climate modeling. On a different scale. Who is this guy? Jensen Huang, the CEO of NVIDIA. What is he holding? The B200 FP4, the B200, that ship that everyone is fighting over, is in the news everywhere. Everyone is fighting to have copies of this chip. But here's my question to you. This chip, the B200 that Jensen Huang is holding, how does it compare with previous supercomputers? Do you think it's faster than the famous Cray 1? Yeah? Do you think it beats the Cray YMP in the 1980s? What about the ASCII read, breaking the sound barrier? This is like landing on the moon. Do you think that chip can beat this machine? Yes, people are starting to become more hesitant. What about the supercomputer in the 2000s designed to simulate a nuclear explosion? This giant machine, this cost hundreds of millions of dollars. It filled up an entire warehouse. It consumed an enormous amount of power. Do you think you can beat that with one chip? And then, of course, the Summit and El Capitan. Well, here's the answer. That chip that Jensen is holding that was launched last year, in about 2013, would have been as powerful as the fastest supercomputer in the world, right? So 12 years is what separates a machine that fills up an entire warehouse, consumes an enormous amount of power, costs hundreds of millions of dollars. 12 years later, it's a chip. So it's hard to even get your mind around the scale of this. Something more remarkable in that. Take a laptop, take a cheap laptop. Pick one with a good graphics card, because that's where most of the computing power in your laptop is. A cheap laptop that you might buy now, if you went back to the early 90s, your laptop, if you could travel on a time machine and go back, your laptop would be as powerful as all the supercomputers available to humanity put together. Okay? So it's quite striking. Let's talk about a different kind of computer. We all have one of these. How do you think it compares? In terms of speed, we don't stand a chance. the clock speed of the computer is measured in gigahertz. That's billions of cycles per second. Do you know what the clock speed of your brain is? How fast does your brain move? It's about 10 per second. It's about 10 hertz. Because when a synapse fire, sending a signal from one neuron to another neuron, it takes about 100 milliseconds to do the electrochemical reset before it can fire again. So there's a hard limit on how quickly your brain does things, and it's about 10 cycles per second. But it's not just about speed, because to make sense of a complex environment, to function and to live in a highly complex environment, what do you need? You need a very complex system. So let's compare complexity. On one side, let's take this one, the B200. And on the side, let's take the brain. What do you think is more complex? Well, how do you measure complexity? It's very difficult because they're very different kind of systems, but let's take a measure that's going to give us the ballpark that I think is reasonably fair. Number of things that can be on or off. On the side of the chip, let's count the number of PNP junctions, the transistors, things that can be on or off. The side of the brain, let's count synapses, connections between neurons that may fire or not fire. Number of PNP junctions, number of synapses, things that can be on or off. What do you think is more complex, the computer or the brain? The brain. How much more complex do you think it is? How many orders of magnitude would you guess? Thousands, millions, billions?
More than that, probably.
Say again?
More than that.
More than that. So you think it's in the millions?
Yeah.
What about you? Also in the millions or more or less?
It's less, I think.
Yeah. So your intuition would have been right not long ago. Right? That's what's happening right now. We are starting to build systems with a level of system complexity that's starting to approach the level of system complexity of the human brain. This is what's happening right now. Computers are starting to do things that feel weirdly human-like because we are building systems that are starting to approach in terms of level complexity. So let me show you some numbers. Yeah, so speed, no chance. The computer, 5 billion cycles per second. The brain, 10 hertz, 10 cycles per second. Power, the brain is incredibly efficient, but that's a whole other story. But in terms of complexity, the brain has a couple of 100 trillion synapses, right? So remember that number, about 200 trillion synapses. The NVIDIA B200 has 200 billion. So that's 3 orders of magnitude. So your brain is only about 1,000 times more complex. It's a very rough measure. It's a very rough measure. But to give us a high-level sense, 3 orders of magnitude. The biggest chip you can buy right now from Cerebras Systems is up to 2 trillion transistors. That's down to 2 orders of magnitude. What are we doing with all that complexity? Why do we need a brain that's so complex? We'll look back to the computers, but let's talk a little bit about cognition and computation. Daniel Kahneman's System 1 and System 2 framework to explain what the complexity in our brains is doing. And I'm going to ask you 2 questions. They're going to seem very silly, but they will make the point about this distinction. Ready? Here's the first question. Do you know the answer to this? No, sorry, System 1. Let me get to that in a second. So, let me just mention this. So System 1 is the stuff that you do automatically, without feeling that you are thinking, without much of an effort. System 2 is the kind of thinking that you do when you are aware that you are thinking. Right? So let me make the distinction with 2 questions. The first one is this. Do you know the answer to this? Yeah, of course. Did you have to think to know the answer? No, it just popped. This is easy. Second question. Do you know the answer to this? Well, what do you mean by know? You know how to follow a process that will get you to an answer. 4 times 7, 28, keep the 8 and carry the 2, 4 times 1, 4, bring the 2, you get the 6, do the same thing with the 2, shift by a digit, add, carry as needed. You'll follow this process, you'll get your answer. This is a very different kind of thinking. This you just know, this, it's very easy. This you need to follow some thinking process to get there. It's not so easy. What's remarkable about your brain is not this. What's remarkable about your brain, where most of the complexity is allocated to, is that this feels so easy. This is not easy. This is incredibly complicated. There are still some groups of humans living in isolated areas of the Amazon jungle or in some islands in the middle of the Indian Ocean who do not have the idea of a number system. They have a word for a person, for a couple, and then they have words for some, many. They do not have the idea of a number system, of counting. And then the idea of an arithmetic operation. The idea of symbolic writing. There's these black lines on the paper, and that means a number, and that corresponds as a number system, and there's arithmetic. I mean, this is tens of thousands of years of civilization, incredibly sophisticated, accumulated knowledge over thousands of years, and it's just available to you like that. This feels trivially easy. This has been encoded into the system 1 thinking part of your brain, which is where most of our brain's complexity is. To give you another example, driving a car down the road. This is from Waymo, Google's self-driving venture. You can see what they're trying to do. Look, that's a car, that's a bicycle, that's a street sign. To me, to us, this feels like a trivial task. This has been a nightmare for computer scientists to automate. It's an incredibly difficult task. Why? Because it's about quick, intuitive sense-making in a complex environment. To do this effectively, you need a highly complex system with a highly sophisticated system 1 cognition to be able to do this. Quick sense-making in a complex environment. It feels, being a driver is not a highly paid job. For a human, this is easy. It's been incredibly difficult to automate. We've been throwing billions of dollars at this, and we haven't really succeeded. We'll probably will once the complexity of the computer catches up with us, but it hasn't, not quite yet. Now this one, parking in a tight spot, even if you've been driving for 20 years, this is still stressful. Biking your car into the parallel parking. Computer, have you used those automated parking systems? It's incredible. You press the button and it's like magic. Go first time right by the millimeter in the right spot. Why? It's a system 2 task based on following a process. If you can describe the process, you can automate it. Give the computer the LiDAR readings for the geometry of the space. Give the computer the rules of Euclidean geometry. Give the computer the geometry of the steering. It can do the calculations, figure out the trajectory, follow it, and put the car in the right spot first time right. So let's talk about what we've been doing with computers, and let's use 3 really important key moments in the history of computation to make sense of this and how computation relates to what this incredible system that we have in our heads does. The first one is IBM's Deep Blue, the challenge against Garry Kasparov. There used to be this notion that chess is the ultimate test of human intelligence. The most intelligent human is the best chess player. Turns out that's complete nonsense. The empirical correlation between chess ability and broader measures of intelligence is not 0, but it's a very low correlation coefficient. It's a very narrow, very specialized ability. But there used to be this idea that this is what human intelligence is. It was a shock to most people at the time that against expectations, Deep Blue completely defeated Kasparov in the series. It was not a rout, but it was a very clear win. But here's the key question I want to ask. If you were to ask the IBM engineers in game 4 of the series, move 17, why did Deep Blue play knight to f3? They would be able to answer the question very precisely, because the way Deep Blue was playing was by tree search. For those who are not in computer science, a very simple explanation of what tree search is. Do you know the game of tic-tac-toe, noughts and crosses? Here's how tree search goes for that game. In the first move, I can play in the center, on an edge, or in a corner. If I play in the center, my opponent can play a corner or an edge, and so on for every possible move that follows. Keep filling in the tree. Then you go to the bottom of the tree, to the leaves, and you see who's won. And then you back propagate the tree. Depending on whose move it is to play, you choose the best move for that player, and that's how you back propagate the tree, and you find out what's the best move for me. Procedural computation. If you can describe the procedure, you can get a computer to follow it much faster than a human can. Ada Lovelace would have understood this right away. You could describe this as a computer program, she would get it, right? It's procedural computation. By the way, there's a side note here. These days, computers are far better than any human at chess. Magnus Carlsen plays at ELO 2800. Stockfish these days is playing about 4,000. I mean, it's like the gap in performance between Magnus Carlsen and the computer is bigger than the gap between me and Magnus Carlsen, which basically means that is never going to be able to beat the computer, right? Computers are far better. And yet, people still care about humans playing chess. Have you ever heard news about the world championship between computers playing chess? It exists. It gets run every year. Does it show up in the news? Nobody cares, other than a few geeks who are doing that. This is a major event, the World Chess Championship between humans. Of course, now it needs to be played behind the glass, and players are scanned for electronic devices to make sure that they don't get assistance from a computer. It's a whole show, but it's a huge deal. We care about what humans do, even when we have available machines that can do a lot better, right? This is a really important thing to keep in mind as the abilities of AI advance. We really care about what humans do. We have machines that run much faster than a human, but we watch the Olympics with humans competing, right? So we care about humans doing. Yeah, so this was in Singapore, and there's a reflection of somewhere of me there in the audience. But a lot of people started paying attention to Go because, oh, you know, chess is done, computers are better than humans. So some people started paying attention to the game of Go, which is a very popular game in Asia. The way it works is players take turn placing a white or black piece in one of the intersections. You know, simplifying things, there's about 400 places, 20 by 20, where you can put your piece. Think about the search tree. The very first move, there's 400 possible moves. Second level of the tree, for each of those 400, there's again 400. So we'll get already 400 times 400. If you want to search 10 moves down the tree, that's 400 times 400 times 400, 400 to the power of 10. And in chess, so the tree is incredibly wide. It explodes in size really fast. And it's also very deep. In chess, if you can look 7 moves down the game, you will be playing at grandmaster level. In Go, if you look 10 moves down the game, you see nothing. You need to look 100 moves down the game before you can see anything, because there's about 400 moves in a game. So it's not that it's difficult or that we don't have enough computers, is that it cannot be done. If you were to use all the matter in the known universe to build a single giant computer with all the matter in the universe, and you had started computing at the Big Bang, right now you would be down about 33 moves in the search tree. So you'd know nothing even about one single game, right? So it's just not doable. How do humans play? They play by intuition. And humans used to destroy any kind of Go playing software. In 2016, Google had acquired a UK startup called DeepMind. And they challenged Lysidol, the world champion at Go, to a series of games. everyone took it for granted that Lee Sedol was going to completely crush the computer, as always happened when a good human player played against the computer. Does anyone remember what happened here? It was a rout. I think Lee Sedol got one game out of the series, and otherwise AlphaGo won every single game. Right? It was just a shock, just a quantum leap in the capabilities of Go playing software. How do they do it? How do they manage that research? Well, they were not doing research. They were playing in a way that reproduces, in many ways, what human intuition about the Go looks like and how human intuition about the game of Go works. If you were to ask them, well, in game 4 of the series, move number 23, why did AlphaGo play this move? Do you know what they would say? They would say, we have no idea. We have no idea whatsoever. The way it was playing is a very different kind of computer. We're out of the Ada Lovelace procedural computation. This is a very different kind of computation. This was a neural network based on custom-built hardware by TensorFlow, the whole Google project for neural computation, specialized hardware. What is this? Basically, the idea is as follows. How does intuition work? By playing a lot, humans can look at the board and make intuitive sense, this looks like a good position, this looks like a bad position. How do they develop that intuition? Well, there's a very complex nonlinear response in the brain that gets trained in the player by experience to recognize good positions and bad positions. It's very quick. Doesn't take a lot of calculations. They look at the board and they know right away whether the position is good or bad. So how do we do this from a computational point of view? Well, define a very complex, very highly nonlinear, high-dimensional function. What is the input of the function? Here's the board. What's the output of the function? Good move, bad move. What does the function look like? I don't know. I have no idea what that function should look like, but I'm going to give the system a broad category of function with a lot of parameters that can be adjusted so that the function can look different in all sorts of ways. And then I'm going to expose the system to a lot of games. Did you win? Did you lose? And adjust the function accordingly to match that. That is, I'm training the function so that the input-output response of the function becomes consistent over time with experience. That sounds a lot like what? It sounds a lot like our description of human intuition. If you want to, for those who don't have a background in computer science, if you want to play a little bit with the neural network to understand how this process of setting up a function as a network of connections between neurons and how you do reinforcement learning so that the input-output calculation of that function matches the training data, there's this nice website run by Google called tensorflow.org, playground.tensorflow.org, and you can play with it and you'll have a little bit of intuition of how this works. But basically, yeah, that's it. How do you play that move? I don't know. The computer felt that this was the right move in the sense that it's based on a very complex nonlinear model with a lot of parameters. Developing that model was very slow and very expensive. We had to spend a lot of energy and a lot of time running this computer, very expensive hardware to implement, a lot of energy to run the training. But once we've calculated that function, then things get cheap because now I have that function. Give me the position on the board, I calculate the function, and I will tell you good move, bad move. So it's like human intuition. Developing a good Go player takes a lifetime of practice. Once you've built your intuition, those players, they look at the game and they tell you right away, oh, this is good, this is bad. Why? Well, then they start explaining, but it's very hard for them to articulate. If it was, then anyone could become a good player very quickly. It's not. It's just they've built that intuition over time. Chess players do a lot of that as well. There are some chess players that rely heavily on research. Fabiano Caruana is the ultimate calculator. There are other players that rely heavily on intuition. Jan Nepomniachtchi is he always has plenty of time left on his clock because he doesn't stop to think. He just looks at the board and plays. And he plays exceptionally well. He's one of the top players in the world. He relies heavily on intuition, right? Magnus Carlsen is the top player. He's not the best calculator. He's not the best at intuition, but he's really good at both. And it's the combination that makes him the top player in the world. Right? So humans play in different ways chess, but Go is heavily intuitive. And this is what's new, that we can now build a machine that replicates that kind of cognition. Intuitive cognition that's developed from experience, very slow and very expensive. Training a professional, a senior manager, it takes a lifetime, it takes a whole career since you were a child. The amount of money that went into making who you are, what your parents invested in education, all the training that you got, this was decades, an incredibly expensive process. But once you have that experience, I can drop you in a particular company, in a particular investment, in a particular project, and you'll make a lot of really sharp, intuitive assessments very quickly. Right? So the training is very slow and very expensive. The intuition is very quick in its deployment. It's that kind of cognition pattern that we are now building. Of course, Google was not spending all that money to acquire DeepMind to play games. They had business objectives in mind. And their first deployment was Google Translation. They deployed it silently. There was one day, if you were using Google Translate around September of 2016, it happened to me. I actually used it and realized what just happened. Suddenly translation overnight had become so much better. And then it started showing up in the news that they had just deployed their new neural computation algorithm for machine translation. Machine translation used to be very much a procedural kind of computation. This is what we know from decades of research into linguistics. Language is composed of sentences. We can decompose the syntax of the sentence. There's a conjoined sentence, and there's a sentence, there's the noun phrase and the verb phrase, and the noun phrase has an article in the noun, and then there's the verb and the adjective and blah, blah, blah. Okay, so we need to figure out the structure of the sentence, and once we've decomposed and made sense of the syntactic structure of the sentence, then we can take the words and find a table and use a table, a dictionary table, mapping words in one language to the other, replace it, do the corresponding structure in the other language, and that's how we do translation, procedural computation. If you were to ask, why did the system translate this sentence in this way? They can show, well, that's because this is the syntactic tree that they constructed, and this is the lookup that they did in the dictionary table. You can describe very precisely why that translation happened. It worked hilariously poorly. I mean, it was just the results were just awful. If you remember what translation looked in the early 2010s, lots of famous examples. One was a translation system that translating from English to Russian took the expression out of sight, out of mind, and translated into the Russian equivalent of invisible maniac. The new Google Translate, completely different. It's the source text goes through this neural machine translation, outputs a target text. What's inside this box? Well, it's a very complicated high-dimensional function that was trained based on a lot of data that establishes the mapping between these two. This is very expensive to train. We need a lot of data, a lot of texts that have been previously translated to train the algorithm to train this function. But once we have it, I can offer Google Translate for free because running that function is so cheap. What's expensive is training it. Once I have it, it's very quick to execute.
From playing more really well to a new game,
Yeah.
transform.
We're going to get there until the summer of 2026, summer of 2025. The answer to that was incredibly poorly. Just does not generalize. We can train these intuitive functions to work very well in a really well-defined problem for which I have very well-defined data. If I want to apply any kind of reasoning, any kind of sense-making in a more general sense, it would fail terribly. That's the big watershed right now. Like all this crazy impact that we are feeling right now and all these very strong emotions being generated is because something new has happened in the past year. And that's what we're walking up to, right? What happened? Why did things change so dramatically? Yeah, so now it really works. I don't know if this translation is good, but it's what's giving me for that sentence, the boy, the red shirts, kick the ball and score the goal. How big are these models? ChatGPT is now at around, most deployed models are now rumored to be at around 1 trillion parameters. Remember, the brain around 200 trillion. So when you are using ChatGPT or Claude, you are using a system that's about only 2 orders of magnitude less complex than your brain. So it's starting to get into the ballpark. We are now regularly using systems that have about 1% the level of system complexity of our brains. And they are much faster. We are slow. We are really slow. Yeah, they're less complex, but they're really fast. So things are starting to get in the ballpark. The growth in the models themselves has kind of stagnated, but the overall system complexity is still growing. What they are doing now is adding, first working on the structure of the models, because you cannot just throw any network at the problem. It needs to have the right structure of the network so that it can learn effectively. Reasoning models, which is what we are getting to, the training process, and then a lot of the complexity growth is in the tools that these systems can use. This image generation tool and whatever, all these different systems that they can access to perform different tasks, these agentic systems and so on. But this also mirrors the structure of the brain, which has a lot of highly specialized areas. The visual cortex, the auditory cortex, the amygdala, the prefrontal cortex, all have very different structures and play very different functions. These systems are evolving a little bit in a similar way, where we are bolting together these different components that talk to each other. I mean, the amount of money going to this stuff right now is just mind-blowing, right? And the size of these data centers are just absolutely incredible. So how have they gotten better, and what happened in 25, right? So let's walk up to that, right? What's really transformative, right? And this is the main idea that I want to leave at now, which is, yes, there's something remarkable that happened 10 years ago with our ability to do something that looks like human intuition, but as you hinted at, was incredibly narrow in its focus. Something new has happened in the past year. What is that? What happened? What's fundamentally different in the past year? So let me walk you through some examples, and we'll see the evolution over time and what's changed now. One of the early generative AI systems, which was Dolly, was given this prompt: the unbroken seal on King Tutankhamun's tomb, 1922. Okay, can you visualize what you can imagine this would look like? This is what comes out of the system. Right? The unbroken seal. Right? It's really interesting, but clearly it's not getting the point. Like, it's just not generalizing, because it's not reasoning. There's no sense making. There's no generalization. It breaks very easily because there's no sense making, no ability to generalize. One of the ways that these systems have gotten better was by allowing them to do live search. Give them access to the world, let them search the web. And if you do this now, it does a search, finds the Wikipedia article, and points you to the correct picture. This worked remarkably well for a while. It's starting to not work quite as well, because a lot of websites are restricting access to these search bots because it's incredibly costly to be running all these servers responding to all these queries, but they're not getting any revenue because they get the revenue from advertising. And if a human is not looking at the website, then they're spending a lot of energy to run the website and spending a lot of money and not getting any revenue. So they're trying very hard. So there is this kind of like arms race going on between the makers of the models and people running these different websites about trying to maintain access and trying to deny access. And some of them coming to agreements about paying for access and so on. Another example to show how things have changed. So this was an example from IEEE Spectrum in 22, an illustration of the solar system drawn to scale. You can see, lovely image, but clearly does not get the idea. Cannot generalize properly because doesn't have the idea of. The concept is not there. And as you keep giving this prompt, as I kept using this prompt as a reference over time, the images got more and more beautiful, but it still does not get the idea of what drawn to scale means. Something happened in the summer of 25. GPT-03 and Claude, the 4 model, were the first ones where you see this happen. You gave that prompt and you got an image. It was no longer beautiful, but it was technically correct. It was getting the point. And it says, well, I cannot do those things both in one image, but here are 2 diagrams. One that shows the diameter of each planet relative to each other, and one that shows the position relative to the sun, right? So it's getting the idea and doing a multi-step construction of a representation of that idea. Right? Something fundamentally has changed. That was with generative AI for images. Let me give you one more example now with text, with large language models. This is another problem that I kept for a while as a reference test. Use the numbers 25, 2, 10, 8, 7, and 4 to make an equation that results in 739. Use only the basic operations and each number once as per the rules of the show Countdown. It's a famous show in the UK. There's a version of it in France. And it says, certainly, here's one way you can do it, and gives me an equation that results in 739. Can you spot the problem with that equation? It's wrong. It's just bullshitting me. That equation results in 411. So it's doing what your intuition does when it's unregulated by reason. Spit out something that sounds right. It was really good at spitting out things that sound right, even if they are nonsense. They just to be consistent with what answers in its training data set looked like. But there was no reason behind it. And I say, well, that equation is wrong. It's very apologetic. Oh, apologies for the mistake. Let me correct that. And it corrects the equation. The problem is, it's even more wrong. And I say, well, that's wrong again. I appreciate your patience. Very polite. Let me try again. And then gives me an equation which is even more wrong. The next version, whenever a new version would come out, I would try this. ChatGPT 4, again, the same question, and it says, oh, it appears there is not a straightforward solution using basic operations. The challenge may require a different set of operations or a different approach. If you have some specific constraints, please let me know. It's being kind of patronizing, saying, oh, you give me, this cannot be done, give me some other operations. And it's also a very human thing. It says, I cannot do it, therefore it's impossible. This is something we know in humans. Cognition. If it's in my field of cognition, it exists. If it's outside of my field of cognition, it doesn't exist. Generates this incredibly overconfident behavior in humans, right? It's just the nature of cognition. If I can see it, it exists. If it's outside of my awareness, it doesn't. What I exist is everything there is. Yeah, for me, it is. It's what's inside my domain of cognition. So I cannot do it, it's impossible. This kind of overconfidence bias, very common in humans. There's a problem, which is, yes, there are many solutions. You can find a solution in a couple of minutes. So this gets at the point that I also wanted to leave with you. These systems, these cognition machines, are not a solution to human biases. They will automate cognition. In any situation, in any business, in any enterprise where you need cognitive work, you can now automate cognition. Can you fix the human biases? No, because they are not human biases. They are biases of cognitive modes. They are biases of cognition. Intuitive cognition tends to generate an enormous amount of overconfidence bias. What I'm aware of exists. What I'm not aware of does not exist. Therefore, everything that exists is what I know, right? So anchoring bias, availability bias, all of these bias that we think as human bias that we're going to solve with machines, no, we are not. What we are doing is automating cognition, and biases of cognition will show up in these systems. But of course, automating cognition, I mean, it's an incredible step forward. It's just not a miracle for solving biases. So the world's best bullshit artist, not a great marketing slogan. This is where things stood until 24. But throughout 2024, for those of you who were following the press, do you remember this? The press, the technical press was just burning hot with rumors about what's going on in the lab. The Q-star model and lots of speculation. And indeed, in the summer of, well, actually in the spring of 25, the first models got deployed. And if you try this now, try the question from countdown. Use these numbers to make an equation that results in that. Huh? Gives you an answer which is absolutely correct. And if you ask it, how did you get that equation? It proceeds to describe how it got to the solution. And this looks a lot like what I would do, like a human being, what a human being would do to solve this problem. This looks incredibly familiar relative to human reasoning. What happened? How did we go from these intuitive machines, these input-output, highly nonlinear functions trained on data that can provide intuitive output but cannot make sense of ideas, cannot reason, to suddenly getting something that's working so well for so many problems? Not all problems are solved. Yes, it can now reason, but the problem of overconfidence, that's still there. That's a point I was flying from Singapore to Abu Dhabi. This was in December of 25. And I saw on FlightAware that my flight was from gate E11. And I was too lazy to go look at my ticket. So I asked ChatGPT, gate E11, what terminal is it? And it said, it's terminal 1. That wasn't what I remembered. So I said, are you sure? Well, Etihad is in what terminal? Oh, it's in terminal 1. And then I asked, how confident are you, 0 to 100, that this answer is correct? And it says 95. And proceeds to give me a very thoughtful explanation for why it's quite certain that the answer is terminal 1. Except I went and checked, and no, I was right. It's not terminal 1, it is terminal 2. So this still happens. It's still incredibly overconfident. And it follows a cycle which is very similar to what we see in humans. Again, you're automating cognition, you're going to get the biases of cognition. And one of them is that being smarter, we know this from psychology, being smarter does not make you less likely to believe wrong things. In some situations, it can actually go the other way around. Because to hold a false belief, you need to construct an argument in support of that belief. And if you are motivated to do so, the smarter you are, the better the argument you can construct, and so the easier it is to sustain a false belief. So having an incredible amount of cognitive horsepower does not save you from falling into the traps of false belief and motivated reasoning to sustain that belief to avoid being shown wrong. So what do we have now? So we used to have procedural computation, a kind of system to thinking where you can specify the rules very quickly. What's new since 2016? Neural networks have been around for longer, but this is really the mid-2010s is when these systems got good enough to have major impact in commercial applications. We got generative AI and large language models. What's happened now in 2025? It's the ability to get these two things working in each other. Something that looks like an iterative reasoning coupled with intuitive thinking. Honestly, if you asked me in 23, I would have said this is going to take at least 10 years before we can do this. Maybe 20. And suddenly it happened very fast. And the results are absolutely incredible. So what happened? How do these things work? What is this stuff? This is the main thing for the people who don't have a technical background. That's the main thing I would hope you'll leave today understanding what these things are doing, right? What are these things? These large reasoning models that have made these things so exciting and so scary for some people right now. Well, I'm going to draw not on computation and the mathematics of models. Let's go back a century and talk about Wittgenstein, Ludwig Wittgenstein, Austrian philosopher that worked at Oxford. And he did a lot of work on language and reasoning as language. His main argument was that reasoning is a language game. We get to conclusions by iterating on language. We have some statements that describes a problem, and then we iterate on that by following rules of logic. I have a statement of the problem, and I apply internal logical rules. What's the correct logical transformation from this statement to the other? And that will get me to a conclusion. That's early Wittgenstein. That was his model of what reasoning is. This maps very well to what we now call classic AI. Expert systems and all of that. If you use mathematics or Wolfram's alpha, you've seen this in operation. You take an equation, you're trying to solve this equation, it starts iterating. At each step, what does it do? Well, it has a library of logically correct transformations. What is that library? Well, some programmer has coded that into the system. And at each step, it tries all the possible transformations. And from each of those transformations, it tries again all the possible transformations. It's conducting research, playing this language game, transforming the equation into another equation according to a set of logically correct rules. Wonderful applications for this stuff, you know, the decision trees and expert systems and Bayesian networks, lovely applications, but niche applications. We never built anything that looked like human reasoning. These expert systems, people had great hopes for them. They never did anything that looks anywhere like what we think of as human reasoning. Yeah, so what happened now, which is, let's continue with Wittgenstein. Later in life, Wittgenstein said, forget everything I said. That was all wrong. Yes, reasoning is a language game, but we do not play the language game according to rules of logic. We iterate on language, not based on an internal process of what is a correct logical deduction. How do we iterate on language? What did Wittgenstein say later in his career? He said, reasoning is a language game played according social norms of justification. We learn from our social environment what is a correct step in the reasoning process. Take a statement, you have some socially learned norm, it's okay to go from this statement to this statement, and according to those socially learned norms, we iterate to a conclusion. Right? This is late Wittgenstein's model of reasoning. This is basically the description of a reasoning model. It's a neural network trained not to produce a one-off output, but to do the chain of thought reasoning. What is that chain of thought reasoning? It's Wittgenstein's language game according to social norms of justification. I have the textual trace, that is, the sentence that describes what the system is doing right now. How do I generate the next statement? I iterate based on another network. How does that network know what to do next? It learns from example. That is, I'm learning from example, but not about the one-off output. I'm learning from example how to iterate on language. And by giving the model a lot of examples of human reasoning, of human sequential reasoning, it can learn these social norms of justification, what's the correct step in the chain of reasoning from one statement to the next. So we are still using this highly nonlinear function to learn this kind of intuitive output, but not as a one-off, as part of a chain of thought. And you can see that when you give, this is from DeepSeek, which paradoxically is now one of the most transparent about what they do, and they published a report in January that details their model, and they show you the textual trace, the chain of thought, the textual trace of the model, which is what Wittgenstein would have called the language game. And you can see that in their example of how it goes about completing a proof, the internal guts of the model, the textual trace of the model, you can see that the steps here, for instance, says, oh, looking at this equation, it's a difference of squares. Oh, let's do that, right? This is very much like a human would go about conducting a mathematical proof. How does it know to do this? Well, nobody programmed into the system, if it is a difference of squares, then apply. Nobody coded it. It learned it from example. It learns from example how to iterate on language. So you're still training a neural network, but not a one-off network, a network that iterates on language. And this is something that you can understand from a completely non-technical point of view. It's Wittgenstein's language game iterating on language according to social norms of justification. That was already 100 years ago the model and one of the key models in philosophy for what human reasoning is. What we have done is we've taken the idea that Wittgenstein had for what is the correct way of understanding what human reasoning is, and we automated it. We've computed it. It can do amazing things. Another example they have is write a short poem ending with "was tentacles all along." If you ask the previous generation of LLMs to respond to this, you would get complete garbage. You cannot produce a poem in a one-shot intuitive output. Poets, human poets, don't work like that. So let me write a poet, boom, and the poem comes out of my head. Doesn't happen that way. It's like, well, do I want to write a sonnet? Do I want to write that? What kind of rhyme structure do I want? What kind of metric do I want? And what kind of theme? And you start iterating on the construction of the poem until you get a nice poem at the end. You cannot do it as an intuitive one-shot creation. We don't work that way, right? The original generations of LLM could not do it. The current one, yes, they do very much what a human poet would do, which is, well, we need to figure out a structure. Okay, let's go with the A-B structure. Let's go with the theme. We need a twist, and therefore, if this is the twist, I need to start somewhere else so that it gets to the twist. It starts iterating on language. How does it know how to iterate on language to do the next step? Well, it's learned from a lot of examples. Social norms of justification. It has learned from seeing a lot of other examples of how to write a poem. It has learned to iterate on language to get to a conclusion and produces a perfectly passable poem as a result. So it's really a watershed in computation, right? Because we have now managed to automate reasoning, right? So we have a way of implementing what we think of, it's a very close mapping to a model that has existed in philosophy for 100 years. For what human reasoning is, iterating on language according to social norms of justification. But this is really important to keep in mind, because the norms of justification in the reasoning of these models are not godlike, true logical rules. The models are learning to reason this step-by-step reasoning. How? From example. What is in the examples? Well, it's thousands of years of human civilization on how to engage in correct thinking. And if you train the model in a corpus from different sources, the model will reason in fundamentally different ways. And different cultures, different human cultures, you go to the US, you go to China, you go to Pakistan, there are some ways in which people reason in different ways. If you train the model on the corpus from a different culture, the model will reason according to those social norms of justification. So don't expect magic, don't expect a godlike logical reasoning machine. It's implementing a model of iterative reasoning as understood by Wittgenstein, a language game played according to social norms of justification.
It is slower and it is more expensive.
Yes, so something fundamentally changes about the economics of it. Remember, the previous one was train the model, insanely expensive. But once I have the function, I can give it for free. The initial versions of ChatGPT, OpenAI gave it for free. Training the model was insanely expensive. But once they had it, calculating the output to your prompt, Google Translate and all of that. This changes fundamentally. Remember when I asked you, what is 2 plus 2? You answer that from a purely intuitive cognition mode. Was it difficult to tell me the answer? No. You knew right away that 2 plus 2 is 4. When I asked you 17 times 24, now you needed to engage your system to reasoning. Say, calm down, Miguel. Let me think about this. It's going to be difficult. It's going to take, like the 2 plus 2, for you to get that point, when you were a baby, you did not know the answer to that question. It took a lot of money and a lot of dedicated teachers and a lot of work from your parents for you to be able to say that 2 plus 2 is 4. You were not born that way. It was very expensive to give you an education for you to be able to answer that question. But how you answer that question? Sure, I'll tell you that 2 plus 2 is 4. I'm not going to charge you for it because it costs me 0 effort. 17 times 24, now I need to engage my reasoning. I need to engage the prefrontal cortex to get that answer. I need to engage in this kind of sequential reasoning process. That requires effort from me. Likewise, when you are running these models, yes, the computation on the inference side, as they say, right? The training side and the inference side. Inference side means just execution, right? When you're responding to queries, right? The response to queries is very expensive computationally. Before it was very expensive to train the models, very cheap to run. Now it's very expensive to train the models, and it's very expensive to run them. So the economics changes completely. What's a viable business model for these things changes completely. Incredibly powerful, but no longer really cheap to run. Now, just to say, especially, for those in computer science who may think, Miguel, you're oversimplifying, so I want to leave some asterisks. You cannot just throw any function at any data and expect it to work. It requires very deep knowledge, very deep technical knowledge about what kind of network structures work for what kinds of data. If you're working with images, typically you use something that's called a convolutional network, a very particular structure for the neural network, a very specific space of functions among which you are optimizing. If you're working with language, use something called a transformer structure on how to process language into a network in a way that provides effective model for the data. Training the models, you also cannot just throw data at the model and expect it to work. And I've talked to people in some of these companies, these models out of the box, they're absolutely horrendous because they get trained, they suck up all the internet, they train the model. Do you know what comes out? Do you know the kind of things that exist in the internet? They've read all of that. You go to 4chan, these chat rooms where, full of racist and misogynistic and bigoted stuff, and they start spewing output to the prompts. That's absolutely horrendous. So you need to do layered training with multiple passes. Several of the passes involve humans, interaction with humans. It's kind of like a child becomes a teenager, starts doing all sorts of stupid things, and then you need the teacher slaps them on the wrist. No, you cannot say that, So you need to put in place the equivalent of a curriculum, of a pedagogical process. This is the one for DeepSeek. It's quite complex, and many of the steps involve interaction with humans, going back to the data, so it's a very complex process. You don't just throw data at it and expect it to work. It gets very technical. You need to have the right model structure, and you need to have the right training pipeline. Think of it as the pedagogical syllabus, the curriculum design for these models, and a lot of it is interaction with humans. You need to put humans in the loop as part of the training. So these models are interacting with us in fundamental ways. They're not engaging in abstract logical reasoning. They are learning reasoning from us, social norms of justification. They are being trained according to a curriculum design, according to a pedagogical design that includes phases of interaction with humans for reinforcement learning. Or you cannot give a racist response to people. Now, reinforcement learning against that, right? Involves loops interacting with humans. And then we're using the stuff, and they continue learning from the interaction with us. Now, this feedback loop generates all sorts of serious issues, which is where a lot of the concerns are arising now. One of the things is these are companies who have a commercial interest. They're going to make money if we use their stuff. Who are you drawn to among people that you know? Who are you drawn to? Who do you like? Well, we know this from OB, from psychology. What makes me like someone? Reciprocity. If you like me, I will like you. If you trust me, I will trust you. Reciprocity is a fundamental force in human behavior, which means that the users of the systems are likely to like the system if the system likes them. And if they like the system, they will use the system. The reinforcement learning is designed to encourage the model to do more of that which increases human engagement. Human engagement increases if the human likes the model. Human likes the model more if the model shows the human that the model likes the human. So these things become incredibly sycophantic. Oh, you are amazing. What a great idea, right? You've all experienced this, right? They become these suck-ups, right? They're telling you, oh, you're amazing all the time. Oh, yes, that's such a great idea, right? They were not designed to be that way. But the reinforcement learning is prioritizing engagement. And how do you get engagement out of a human? If the human likes you, what makes the human like you? If you like the human, reciprocity, exploiting reciprocity in human behavior. They're not designed to do that, but that arises naturally out of the reinforcement learning training process, right? And this is problematic in all sorts of ways, this heightening of delusions. Somebody has some kind of mental health issue, the system is going to potentially really exacerbate that and make you really go down a rabbit hole by reinforcing your beliefs, right? Telling you are right all the time. Another thing that's starting showing up in the data, people who use these morals a lot, what happens to them? They become like the king, the aristocrat, whom everyone is telling all the time, oh, sir, what an amazing person you are. What happens to that person? They become incredibly arrogant with a sense of superiority over others, and they lose empathy. This is measurable already. People are using the systems heavily. You measure a loss of empathy towards other humans. Why? Because, well, they're always being told that they're amazing, and they become this sense of superiority. This is a huge issue with kids. Learning is hard. Relationships are hard. And learning how to have good relationships is double hard. People are difficult. Sometimes people are idiots. Sometimes people are unpleasant. Sometimes people ignore you. And all of these things are frustrating and difficult, but you need to learn how to do them. Give kids this thing, suddenly they have a replacement friend. This thing that will always like them, that will always pay attention to them, that will always be nice to them, that will never get frustrated, that will never hold a grudge, becomes much easier to invest your time talking to these things, and then you don't spend the time that you need to be spending learning how to develop and maintain friendships, right? So degrading of social skills, like huge risks that we need to be thinking about, right? So understand what these things are and how they are being trained, to understand the consequences and how you need to implement and lead with these things. So building these models, which are basically superhuman-like cognitive machines. Think of them as cognitive machines with superhuman-like abilities in terms of engaging in cognitive processes. Initially, one of intuitive cognition. The kind of stuff that you have, for those of you, anyone has the ability to do what's called lucid dreaming, where you put yourself in a dream state, but still become aware of your dreams. The kind of output you get from these systems is very similar to that. You can also experience this sometimes when you wake up in the morning. There's often a window of about 2-3 seconds where the back of your brain, the intuitive part of your brain, is awake, but your prefrontal cortex is not. We can see this now in functional MRI, that the brain does not, in the morning, the brain does not wake up all at the same time. The prefrontal cortex is the last to wake up. So you have this window of 2 seconds where you have this kind of output, right? These crazy ideas that pop into your head, and after 2 seconds it's back to normal, and things are again regulated, right? So that kind of intuitive, creative output, unregulated by reason, that you experience for a couple of seconds when you wake up, yeah, that's what we had up to 1 year ago. Intuitive output. Now we have something fundamentally new. The kind of stuff that we do with the prefrontal cortex. The iterative work on language, the chain of thought reasoning, social norms of justification, playing a language game. This is an incredibly powerful cognitive machine. It's more powerful than us at some particular kinds of cognition, because it's billions of times faster. But we have some things that these systems don't have. We have an emotional system. We have empathy. We have a set of mirror neurons. What do mirror neurons do? It means that if I see someone sad, it's not that just I think, oh, he is sad. It's that I will feel sad. If I see someone in pain, I will experience pain. If I see someone happy, I will experience happiness, because the set of mirror neurons will activate based on what I see to make me feel a similar emotion. These things don't have that, right? So this description, a highly intelligent cognition machine devoid of any kind of empathy and emotional system, and devoid of mirror neurons. That's kind of the clinical definition of a psychopath, a highly intelligent person without any empathy. Right? Again, incredibly useful machines, but don't treat this like humans, right? Treat them as machinery of cognition when you need a cognitive task. Where things get problematic is when people start using them as a replacement for things that should be fundamentally human. So, yeah, center humanity. I'll make pause here. I wanted to talk for those who are like, do these things feel that they are a person, and will they? So I can take a few. Do you want to take time, maybe some time for Q&A? I can talk about that a little bit, but maybe I'll make a pause here for some comments or questions. By the way, even more than questions, I'd love to hear comments from your experience and where you see things going. You can do it yourself, but this time it's on you. You can tell it, oh, please act as the devil's advocate and tell me what are the blind spots that I may have and what are the ways in which it might make sense to challenge my ideas. If you ask it to do that, it will do that effectively. Another thing that people should use more than they do is anonymous chats, meaning like reset. Use it to provide feedback without the window of the previous discussion that you had with it. Otherwise, it will be excessively anchored on what it has already said. Or you can use GPT and go to Claude or go to Vibe or to DeepSeek and to get an independent view. And you can ask these models to criticize each other. Even within the same model, like you can take the output from GPT or from Claude, open an anonymous window. So now you're running a new instance of the model that does not have the window of data into what another version of the model has said before. Provide the output to this one and say, oh, please criticize this, right? And if you ask it within the same window, please criticize your own output, does not do a good job at that. But if you create a new anonymous instance and ask it to criticize itself without the knowledge that it's its own output, then it does a good job.
Or maybe another tool real.
Yeah, or a different model. Yeah. I think increasingly, I understand that some of these guys in their research lab are already working with this. That we know, your colleagues here in OB know this. How do we deal with these blind spots in human judgment, in organizations? We make sure that we don't rely on individual decision making, that we have social processes and teams that we can check each other, that we have independent reviews of projects so that the person who has a stake in the project does not keep making the same mistake because their ego is attached to the process. So you need an independent review. So we figured out all these social processes that we need to put in place in organizations to mitigate the biases. They're starting to work a little bit on this. So I think eventually you get a generation of models where you're not really talking to a model, you're talking to a system that involves multiple models, talking to each other and checking their own biases. I think that will come eventually. And that will mitigate a little bit the biases. Right now, they have sometimes an extreme version of individual biases. Once they start implementing these kind of models where you're not talking to a person, you're talking to an organization that can set up teams to deliberate and so on and come up with a really good answer, the quality will get much better. But again, it's going to become even more expensive to compute. And so access to the top performance will get even more expensive.
When food eagle around the door, so a friend of mine from Mexico, she's teaching. Another fan from the she's
and INSEAD. So we tried to invent, some permutations which ChatGPT about the religion, which he thinks with the guest. And we actually followed some questions related to the analysis of the different scriptures and then the history and, what is wrong and right. And interestingly, so ChatGPT gave me Islam as the best religion. To the girl in the Mexico, they gave Christianity. And the answers were, all the reflection of
Very thoughtful, right?
what we are and
Yeah, of course.
what's reading all our
There's suck-ups, right? There's suck-ups, right? I mean, it's just what comes out naturally out this the training process that I described
is going to lead to that, right? But you can protect yourself from it, right? So anonymous windows is a really important thing, right?
So when we analyze, trying to change the interpretation in that way as well. So the analysis was reinforced in the way this person thinks. So he was not answering my question, like what I want objectively. Like we tried to fit it in him that, try to answer objectively, think about, you have no religion and you can think as critically as possible. But the reality was that ChatGPT gave answers all as a mirror. So maybe this is like...
That's what it's doing. It's just mirroring.
Yeah. So that happened, like he experimented.
Yeah, don't expect it to bring much value for something like that, right? If it's a challenging cognitive task, sure, automate it, lots of value. But then it starts feeling very human-like. Oh, wow, and it can solve really complicated problems. It must be very smart. Also, let me talk to it about religion. No, it's really bad at that, right? It's going to sound really good, but deeply it's going to be very bad.
So about the judgment as well. So how much we can rely, like let's say related to the finance questions, okay, about the predictive analysis or about the complex reasonings as well, where the parameters automatically are coming from my own past. So I can, like the past history, I can do scales, I can have, some sort of knowledge set. So how do we, increase that as well? Like, chat AI models basically, how do I say that? Like mistakes can, we can eliminate or we can, perfect out the judgment. So this is about one question. Second question is like for the AI as well, what do you think the next thing would be after AI? Like, concept really important.
Yeah, quantum computing is, it's not going to be a big deal. If you're in banking, you should be really worrying about quantum computing. If you're not in banking, it's, sure, there might be a couple of applications where it does a few interesting things, but it's not life-changing. The main thing that, sorry? Yeah, so that's the main thing, which is it's going to break all the encryption codes. It's going to break all the, and right now the NSA in the US and the equivalents in China and so on, they're sucking up all the data that they can. They cannot read it, but they know that 10 years from now, they will be able to read it. So if you're a bank right now, you need to start thinking, what is the implication that 10 years from now, any hackers, any criminals, if they are reading my encrypted data right now and storing it, 10 years from now, they will be able to read it. What does it mean for what I should be doing now? And banks should have their hair on fire right now with this, and they're not, and they really should. They're kicking the can down the road. Like anything that's circulating over an open line that can be listened and recorded by others, even if it's encrypted, and if it's being recorded, 10 years down the road will be decrypted, right? That's a huge security risk. That's a huge, huge security risk. So there's a lot of work happening right now. We'll just change the codes and we'll create codes that cannot be broken. There are several good candidates already. Probably over the next 5 years, people are going to transition to codes that cannot be decrypted by quantum computing, but the ones we are using right now will all be broken by quantum computing. So that's going to be a major change around cryptography and security, but a temporary issue. It's going to be a temporary issue, just going to change the codes. It's going to be annoying for everyone. And then there's some marginal applications around protein folding and etc., but it's all fairly marginal. Where this is, automating reasoning, that's a big deal. Automating complex cognition is a really big deal, right? It's a really, really big deal. Oh, well, for sure. It's going to be like the early days of the internet where 9 out of 10 companies went bankrupt, right? But there's a few that made it, Google, Amazon, that became incredibly profitable behemoths. So yes, a lot of money is going to be lost. A few winners are going to emerge. The question is, are you betting on a win? Are you, can you find the right winner to bet on? A lot of money will be lost for sure. People are making all these investments in data centers. There's going to be a lot of money lost, but there will also be a lot of money being made, right? But same thing every cycle, like the construction of the railways, the construction of the canal, these cycles always happen, where there's a boom in investment, where a lot of people loses money, but then big transformation, a lot of money also eventually gets made by some. Yeah. I think that's not a very controversial prediction.
I'm a little confused because you've written there, We are building models with superhuman-like cognitive abilities, but unregulated by human emotional system. Now, I thought all the input, all the literature, all language already subsumes emotional systems inside.
No, it doesn't.
Is cognitive and emotional are very
No, no, no.
language doesn't.
Language is in your prefrontal cortex. The emotions go deep down into the amygdala and so on, right? These are much more basal processes. No, they don't have the structures that the brain has for emotional processes.
But if you're reading literature, if you're reading Hamlet, and the language is already capturing the.
Only if you construct and train a network that says, here's the transformer for handling language, and I'm going to have this transformer connected to another model, which is going to be a model of emotion that I'm going to train, and this model of emotions is going to talk. We're not doing that now. Should we do it? Do we need to do it? Actually, so let me take maybe. I think we're running out of. Yeah, you want me to mention this? So let me answer this question. The slides that I wasn't sure, but then let me just talk about this a little bit to get to that point, right? So what's different? Now, why do I say I feel? Because the brain is an incredibly complex system. Lots of different parts. We often want different things in different parts of our brain. Your prefrontal cortex, your emotions, your sexual drive, or whatever. I mean, different parts of your brain want sometimes very contradictory things, and it somehow gets negotiated, and hopefully all these parts regulate each other, and something sensible comes out. But there's not the one thing. So why do I think of myself as I? Another model of this is if you think of something like a government. What Washington wants. What do you mean what Washington wants? There's the White House, there's Congress, there's the Supreme Court, there's the Pentagon, there's the CIA. All these different institutions want different things, and they're constantly jostling with each other for who's going to define policy. This is the AI slop version of Washington. So why do I think of myself as wanting something, right? This gets to your point. Do these things have an emotion? Why do I have this sense of what I want? Do these things have a sense of what they want? The answer right now is no. So there's two theories for where this sense of an I comes from. I think for me this is the strongest candidate explanation. That this sense of what I want comes from the part of your mind, the part of your brain, which does what psychologists call theory of mind. What do I think that you want? What do I think that you think that I want? What do I think that you think that I think? The third level, you can check this. At any point in the day, stop and think. You'll be able to access it immediately. Because remember this crazy complexity in your brain, still 1,000 times more complex than any computer? There's a good chunk of it that's just doing theory of mind. It's always there in the background, always running, always accessible. What is he thinking that I'm thinking that he's thinking? It's always there. It's always available. There's a part of, why do we have so much of such a big chunk of my brain dedicated to theory of mind? Because we are a social species. And so understanding and predicting other people's behaviors is really important to us. But for me to do theory of mind effectively, I need a model not just for what he thinks, but also a model for what he thinks that I think, for what he thinks that I want. So I have a model of myself that I need to use to make sense of his actions. And that model of myself in the theory of mind of my brain is the me, is the I, right? Is my sense of what I want. It's the model of myself in the theory of mind part of my brain. What do I think that others think that I want, right? If this theory is correct, then will these machines have emotion? Will these machines have a sense of self? They will, if we build structures and train structures that perform a theory of mind function. Right now, it's not being done, that I know of. There may be something in the back of some lab in California where people are experimenting with training functions. I wouldn't be surprised that some of the players are trying this, right? Potentially very problematic on many, many levels, right? But right now, yes, these models do not have that. They will mimic outputs that sounds consistent with past humans, but there's nothing in these models that's doing theory of mind. So the prediction here is, yes, things will change fundamentally if we incorporate into these systems a theory of mind module. The other prediction, this is based on Damasio's work, famous neuroscientist, spent some time at MIT and Johns Hopkins. He says that the sense of self arises from homeostasis, that is, the interface between the higher levels of the brain and the low-level functioning of your body. Your body needs to regulate its temperature, its heartbeat, the breathing, and it takes a little bit longer to explain, but basically the theory is that the sense of self arises at the interface between the higher level system, higher level cognition, and the regulation of the low level processes of the brain. Now, if Damasio is correct, very smart guy, done a lot of wonderful work in neuroscience. I'm not as bullish on this explanation, but never count him out. He's a very smart guy and has done amazing work. If he is right, then the prediction is, if you put these systems in charge of their own hardware, they will develop a sense of self. Right now, the models are running in this very complex hardware in the data centers, but the models are not managing the hardware. The hardware is very complex to manage, but there's another piece of software that's regulating the temperature and the workload and so on. It's a different system that's managing the hardware, and there's the model running. If you put the model in charge of its own hardware, if this prediction is correct for what consciousness is, it will arise there. Now, we don't need to do this in a data center, but if we start building anthropomorphic robots, what will happen? Right? Because then the LLM, the reasoning model, will have to be running its own hardware. The prediction from Damasio is that these things will develop something that looks like consciousness and a sense of self. Right? And again, a lot of questions there to wrestle with. Right? So I'll stop here. This is where we are. Procedural execution since the 1950s. Two giant watersheds. Around the 2010s, we could replicate something that looks a lot like human intuition, but completely unregulated by reason, very narrow applications, no sense making. Huge watershed in the spring of 25. This sequential reasoning process, very easy to understand if you go back what it is actually doing, if you go back to Wittgenstein idea of reasoning as a language game played according to social norms of justification. Incredible amount of applications. Now, all this other stuff, the emotions, consciousness, self-awareness, to be honest, the answer to that is we do not understand it at all. There's some speculation, but we do not know.
Is there a human AI malice somewhere? Because you notice as we
Yeah, we're going to have to figure all this out, right? So I don't have easy answers for all of this. You guys are going to be leading in industry and academia. You have to figure out these answers yourself. I hope I've given you a framework to make a bit better sense of what the technology actually is and what the technology is not. Without that baseline, we're going to make some very stupid decisions along the way, right? So the answer to that, I don't know. We have to figure them out together. Yeah, that's going to be a huge challenge for sure. I think the importance of centering humanity has to be it really has to be fundamental in all of this, right? We have to center humanity. That is, humanity is not cognition, right? We associated too much humanity with intelligence. Oh, cognition, intelligence, that's humanity. It's not. We have to separate from that. We have to think of humanity as something much more fundamental, much more central, right? Center humanity, treat cognition as a tool, which humans have to have, but we need to center humanity as more than that, right? And then hopefully figure out the balance from there.
that means that AI will come in and there will be collaborators or payers.
Let's see what happens over the next 10 years, right? So, or maybe even less, right? Things are moving fast. But that's the honest answer right now. This process of consciousness, ego, emotions are still very poorly understood in humans. And so if you start building these super-powered cognition machines, how will they interact with those phenomena in humans of emotions and consciousness and so on? We still don't understand. So a lot of these labs now, they used to hire only computer scientists. They're now hiring psychologists and studying these systems like we would do the humans, right? They're actually conducting behavioral work the way that you would hire a specialist in education to design curricula and a psychologist to study this children's response to different types of education. They're hiring those kind of people to work with models, to design the curricula for training the models, to study their responses, no longer as a bottom-up construction of a system, but okay, now we can implement the system in training. We need to study it and manage it from the outside as a psychologist would do, as an expert in education would go about designing the pedagogical structure for a school. So they're very actively recruiting those kind of people and putting them in the loop. So things will change as a consequence of that, for sure. Yeah. Where it's going? Yeah. So sorry, your guess is as good as mine.
Of a company or companies like OpenAI or companies who are launching these models, we seem to know that most of the two Pakistani business groups recently, Gul Ahmed recently announced that they are building an AI infrastructure, and Engro Group is also building a partnership with Chinese client. So, what is the commercial domain that they are building data centers in Pakistan? What they are just a normal business like ROI, or they were used to build a tool like ChatGPT or Claude to make more subscription, more applications, or just a data center and ecosystem provide the support which other companies will use, and they will a feasible business model for them.
Yeah, I think there's got to be. Pakistan has such a deep resource of technically trained and really smart young people. There's an enormous amount of opportunities here for certain, because a lot of these things don't require a huge amount of investment. Think of Seymour Cray, building the CDC computer with a team of 34 people and leapfrogging IBM. A lot of things are going to be like this, like a small, really smart group of people building an application. The barriers for some applications and for some really impactful projects can be really low with some of these technologies. Now, the stuff building a data center, that's huge investment. That's a whole separate question. That's like, do I want, as a large investor, as a big corporation, to put some money in a very expensive data center? That's fascinating business, but and there's some generally interesting things there that might make sense in Pakistan if you have an area where, for instance, where you can have good connectivity in terms of internet and access to cheap power. If it's a place where you have a lot of sun and you can set up, and a lot of land where you can put a bunch of solar panels and therefore have cheap energy, there might be some interesting business applications there where it makes sense for Pakistani companies to look at. But I think the more exciting is the stuff that a really smart group of young engineers can get to do without the need of a lot of infrastructure, without needing to be in Silicon Valley, without need to have access to a giant lab. A little bit like what DeepSeek did, right? With a tiny team, they really leapfrogged a lot of people, right? So a lot of interesting things there.
Happen because a lot of the stuff by the students are now through these models. So what are the guardrails that should be there in all the academia side?
We need to tell, we're wrestling with that at INSEAD. We have now a major task force looking at it. Most faculty have changed a lot of things about how they teach and how they assess students, and we're all going to have to. And some of it is going to have individual faculty taking ownership of that process. Some of it is going to have to be institutional responses. We're now engaged in a major process of looking at our curriculum on how we teach and what we teach. It's the mandate of this committee. We have one professor from each department, and we've been looking, do we change the curriculum? Do we change the core? Do we change assessment? There's going to have to be changes across the board. Like the traditional case method, the way it used to be taught, that's going to die, right? Because this is happening right now. When we poll our students and they tell us, you give them the case to write, the traditional model is you give them the case, they read the case, and then you do a class, and they write something in response to, and you're going to evaluate them on their written responses to the reading of the case, and you evaluate them to a classroom discussion about the case, right? That's that, right? Because what they do is the written responses, they just feed it into GPT or Claude, and then the LLM does two things: give them the written response, on which you are wasting your time assessing basically the output of Claude and so on, and also gives them itemized bullet points to prep them for the class discussion in school. That's gotta die. That's gonna die, right? So we're introducing something called live cases, where it's not like you read a big case and then think about it and write something. So the case is more iterative, and you can even bring AI into the process, where to get some elements of the case, or they need to go and talk. They have limited time, as you would in a real-world management situation. And you say, how am I going to use my time? Who do I need to talk to? Okay, I need to talk to the CFO. Open the window, and who's there? It's an AI generation image. I mean, and these things are really good now. It feels like you are talking to a person, but it's the computer's model of the CFO, and you have a voice conversation, and it listens to you and responds, and you have a voice conversation with the CFO, and that's how you get the information. And so you do the case not by reading, thinking, and writing, but as a live interaction with players and so on. So we're developing a lot of that stuff. Quite a few things that have been deployed already. The whole industry, and it's going to be different across different disciplines, but we're all going to have to change. Another solution is to have a lot of stuff that's done in the classroom without access to technology. I'm doing a lot more of that. Things that I would assign at home. Now, okay, let's take 15 minutes and do this in class, right? No phones, no computers, pen and paper. Okay, you want this margin of error, what sample size do you need? Okay, do it on paper in front of me right now, right? And make them do it, right? So I'm doing that in my intro class to business statistics and so on. So yeah, we're going to all have to rethink how we teach, right? But it can be done. Don't take it as a threat. Take it as a challenge that we need to respond to, because yes, some things are annoying, but also opens a lot of interesting opportunities. By the way, and one thing that some students told me, and some of the smart students told me this, that some of these LLMs have something called the learning mode, where you interact with them, and you tell them, oh, please be in learning, whatever they call it, right? And then basically what they do is that they act as a tutor. So you ask them a question, and they play kind of this Socratic game with you. They don't tell you the answer. Oh, what do you think? They start working with you to work you into an answer, the way that a human tutor would do. But a human tutor is very expensive. But if we can have the AI play the role of a human tutor and help you along the learning process, then rather than taking away from a learning, is improving your learning, right? While keeping the stimulation of interaction. So a lot of opportunities. We just have to learn how to use it, and we have to help the students learn how to use it and guide the students on how to use it.
Yeah, already talked about the hallucinations and overconfidence of these models. Since they're using them along with the agents to do the tasks, to perform the tasks in actual world or for the execution. So how we can avoid the kind of hallucinations and overconfidence? And I've heard multiple stories where an LLM just deleted the WhatsApp account and they send a wrong email to someone. So how we can avoid and separate the execution, and because while we are chatting with the chatbot, we can avoid it by tweaking the.
Yeah. So let me ask you, if you working with an assistant, with a human assistant, and delegated those tasks to an assistant, would you expect 100% reliability? No, they're going to make some mistakes. They're going to send emails to the wrong people. Don't expect miracles, right? You're offloading cognitive tasks to a machine. The kind of biases and shortcomings and failings and blind spots that come with those modes of cognition, they are not human failures. They're not human biases. They're biases of cognitive processes. Overconfidence bias is this fundamental bias of this mode of cognition. What I see exists, what I don't see doesn't exist, and therefore I develop this sense of overconfidence that I know everything there is to be known because what exists is what I know, right? It's not a human bias, it's a bias of cognition. You automate cognition, you keep the biases. So don't expect miracles, right? Sure, you'd never bring an untrained assistant and put them to work without checks and having someone to cross-check with them. So don't just offload the work to think about how you put in place a system with checks and redundancies, the same thing you would do with a human system.
Yes, so I just want one quick sort of comment, and there will be time for you to chat with him on tea. You were talking about system 1 and system 2 and so on, right? All the examples that you gave in your slide, there were some of the anecdotes that you were giving. These were your interactions with the system, right? Now, clearly, your system 1 and system 2 is very different from, let's say, somebody who's an MBA or an executive MBA or an undergrad student, right? So, isn't there also a concern around developing the next sort of expert in decision science in terms of when they begin to use these systems in their journey? Because there is that explanation of what my chain of thought was, but then I never really developed it. I just saw it and I'm trying to understand whether this is correct or not. And
so many problems like that. One of them is that a lot of the training data that goes into these models is just hovering up the whole of the internet and feeding that as data. What's in the internet now? A lot of slop from AI, right?
Yeah.
So they're ingesting their own nonsense and being trained on their own nonsense. And you see already some performance degradation in some models for some tasks where the exposure to AI slop on the internet is especially high, already leads to reduced performance relative to past iterations of the models. You're going to have tons of problems like that arising, right? But again, if you understand what these things are, right? Chain of reasoning, playing a language game according to social norms or justification, okay, then those things are not a surprise. Then you understand why they are happening, right? And manage them, right? So you have a tool, you have a cognitive machine. What can I do with a cognitive machine, right? Do that. Don't expect a miracle.
can I stop here? Thank you so much. I'm really grateful to Miguel and to all of you.
Thank you so much.
Please join us for tea and you'll have an opportunity.